Hey everybody, welcome back. You might recall last year we covered a topic called differentials. Now a differential is just the change in the values of something. How y changes, how x might change, like that. We also dealt with the topic of solving differential equations. We'll talk about that more later on this year. So what we're going to do today is we are going to continue our discussion with solving differentials, but we're going to be using in multivariable. But before we do that, let's kind of review what a differential is. Let's say we have a function, f of x equals 2x squared minus 5x. Of course, it's a single variable. And we want to solve for the differential of y. In other words, we want to solve for dy. Very easy. When we take the derivative of our function dy dx, we're going to get 4x minus 5. I can solve for the differential by multiplying both sides by dx. Therefore, dy would be this 4x minus 5 dx. And this is a differential. And like I said, last year we learned how to solve this by taking the antiderivative of both sides, and we would get the function back plus our constant of integration there. One of the main applications that we learned for differentials last year was a way to approximate values. Now, there are actually two ways we learned to approximate values last year. One, we had the tangent line, and two, we had differentials. So let's say we have this function sine of 0.3, and we want to approximate the value. We don't know what it is, so we're going to solve this two ways. The first way, we're just going to use tangent line. So as x goes from 0 to 0.13, we want to approximate this value. Now, a tangent line was pretty easy. We're going to use the function sine of x. So the first thing we need is a point. And I'm going to pick a value close to sine of 0.13 that I know, sine of 0. So sine of 0 is 0. And I also had to get my slope. Well, of course, the slope came from the derivative, which is cosine of x. Therefore, the slope is f prime of 0, which is just 1. Cosine of 0 is 1. So our tangent line, we would write this as y minus 0 equals 1, x minus 0. And if I want to approximate the sine at 0.13, we would then just let x equal 0.13. And of course, if you solve that, you just get y is about 0.13. This tangent line was very easy to do, but another way we discussed it was using differentials. Now, a differential approximates a different way. It approximates not by looking at the tangent line, but what's happening as a function changes. So if we think about this function, we're starting here at x equals 0, and we're going to x equals 0.13. What we want to find out is how much do the y's change by? Well, we know that the change in x is 0.13. Now remember, this is a known point, right? I'm starting at sine 0. If I let 0, sine of 0, of course, is 0. What I want to find out is this point. Well, I know the x value is 0.13. I just want to find that x coordinate. The y coordinate. So what do I have to find? The change in y. Well, let's take a look at differentials. Well, a differential says if I take the derivative, dy dx, that's going to equal f prime of x. So what my rule is saying to do here is take the derivative. dy dx is going to equal, if I take the derivative sine, I'm going to get cosine of x. So I'm going to get dy equals cosine of x dx. Well, think about what this d stands for. This d of x stands for. That's the change in x values. The dy, that's the change in y values. So I can get my change in y values by finding the cosine. Remember, I'm going to use my known point. Cosine is 0. Multiply that by the change in my x values. Well, my x values are increasing by 0.13. Remember, I'm going from 0 to 0.13. And I can simplify that. That's going to give me, 0.13. That's going to give me cosine of 0 is 1 times 0.13 So I get 0.13. Now be careful. This is not my answer. That is not my y coordinate. This is how my y coordinate has changed. Therefore, to get my new y coordinate, sorry about that. To get my new y coordinate, I'm going to take my original y point, which was 0, add my change in y. So it's going to give me 0 plus 0.13, which just happens to be 0.13. So there's my new y coordinate. Now, one thing I want to point out to you, that's hard to see there, 0.13. These are the same here. They're not always the same because they are solved a little bit differently. So they're not always going to be the same. But this is just a kind of another quick way we can solve. And this is really nice because we can really apply it very well to multivariable. So let's take a look at something we call the total derivative. Let's say we have a function f of x, y is equal to x squared plus y squared. In this case right here, there are two differentials to solve for. There are two derivatives. These are our partials. For in other words, I can solve for the derivative with respect to x, and I just get 2x. I can take the derivative with respect to y, and I just get 2y. Writing these together, we would get our formula. dz, the derivative with respect to z, the change in z, is equal to our partial with respect to x, dx, plus our partial with respect to y, dy. Now, if you think of these as slope, ready? If I get rid of this, this is basically saying z minus z1. If I write this out, z minus z1 equals, this f prime, remember, f prime, f of f sub x, or my partial with respect to x, is my derivative. So this is a slope right there, fx, that's a slope, times my change in x, which is x minus x1. Now, if I think of this as a slope x minus x1, that should kind of look like our tangent line equation. And it is, except for we're just adding also the changes in our y. So plus the partial with respect to y, y minus y1. This is what we call a total derivative because we're including all of the changes, how x and y change in our problem. So I can write this as a total derivative by saying this is going to be dz equals my partial with respect to x, 2x dx, plus my partial with respect to y times the change in y, dy. Now, what does this find for us? This gives us the change or error in the z values. Right there. That's going to give us our change or the error in those values. So let's take a look. Let's find another total derivative. Right here. So we have z. Z is obviously a function of x and y. So to find the total derivative, I have to first find the derivative with respect to x. Y is a constant, so I'm just going to get 2 sine y minus, take the derivative with respect to x here, 6x y squared. My partial with respect to y, careful, sine of y, this becomes 2x, that's a constant, cosine y minus, this becomes 6x squared y. So my total derivative would be the following. dz would equal, just my x's first, 2 sine y minus 6xy squared times the change in x, dx. Remember, this is like my slope formula. My slope times my x minus x1 plus the change in y's, which would be 2x cosine y minus 6x squared y dy. And that would be our total derivative. So let's take a look at another one. We want to find the total derivative here. Now be careful. W is now a function of x, y, and z. So I got to find my partials for each one of those, 3 partials in terms of w. So my partial with respect to x becomes just 2x, everything else is just a constant. My partial with respect to y is 2y, and my partial with respect to z is 2z, or not 2z. And now when we write our total derivatives, dw, this time be careful, here's dz because that's what we're looking at, here's dw, this is going to become 2x dx, sometimes I use parentheses, plus 2y dy plus 2z dz. And there is your total derivative. All right, come back to video 2, and we're going to take a look at some applications. Hope you'll enjoy it. Bye-bye.